and I'm very happy to introduce Kenji. Since Kenji empowers human capabilities using assistive and wearable robotics, so buckle up for a fascinating talk. Not yet a cyborg, but Kenji himself.
Thank you. I was really nervous about that, Bram, how to introduce me about that. But anyway, so thank you very much. I'm very pleased to present that our work, this advancing human capabilities from assistive robotics and wearable cyborgs. This is a kind of like my past 20 years of experiences with robots, which open that very hopeful and also inspiring that futures. So my research question is always what mechanisms drive the recovery of sensory motor functions during the interaction between wearable robots and humans. We love biosignals a lot. Electromyographies, getting the signals from lower limbs to control that robot. And I had also a chance not like to do the work on that, but we contributed some of that startup companies with the commercialization of this robotics. But still, even if this 20 years of work, we still do not understand why robotic therapy restores the function of walking, nor how wearable robot advance human capabilities. So since this is working on this, the equipment, prosthesis device, mobility aid are well commercialized. This is the kind of equipment. But in the era of our robotics, the assisting, like MIT Manus and Heike already introduced that Locomat and Reworks, and there are many robots, wearable robots, and powered prosthesis, robotic exoskeletons. So then I think these two are assistive robotics and robotic devices for supporting daily life, and the robotic rehabilitation for aiding therapy and functional recovery are slightly different. I was working more at the below side of these medical applications. But the impact, which is that I've got from the message from Professor Alan Beltos, the rehabilitation of deficit in sensory motor function may not suppress the cause, but may lead the brain to find new solutions. This was also that impactful that many others too, because we roboticians are more focusing on the lower limbs, not thinking about the whole bodies. So our exoskeleton challenge is by make use of that whole body's coordinations. So like that, how we can try to get that new control mechanism and the structure of that robotics and we're working on. And this time is embodied intelligence was discussed a lot. I was also one of them in the 20 years ago. Professor Lolo Pfeiffer came to Tokyo and I attended to see these videos. It was very amazing about that. Oh, this is passive worker. But we realized on that important things is, of course, this whole body's coordinations. Especially like that, these upper limbs motions. Oh, while walking upper limbs, we naturally use that. So we are thinking about that to transfer this idea to exactly that exoskeletons. We have that many patients with spinal cord injuries, unfortunately not able to get biosignals from lower limbs. But they are very much healthy in the upper limbs. Why not we are getting on that signals from upper limbs and try to transfer signals to the lower limbs? So this is the feasibility study of the 4 spinal cord injuries patient. 4 of them could control from that upper limbs movement to lower limbs that the robotic walking patterns. And amazingly, also 3 of 4 increased also, they are the incomplete spinal cord injury. 3 of 4 also increased the EMG activities after the sessions. So still, we don't know why, but we have many of the human capabilities, the potentials. So not only that the legs, but we work on a lot of different type of the robotic exoskeletons. Application to the shoulders, and also application lumbars. Not only that the motors, but we use some of the functional fluid. Neck is also the patient with dropped hand syndrome. Face is for the patient with facial palsy. There are lots of the bodies which has the problems. But still, robotics is able to help and assist those kind of the people. This is one of my favorite work of the robotic face mask only 1.5 newtons of just like pulling the muscles by using that healthy side of the face biosignals to feed to control on this. These patients has the problem of the motor functions, but not sensory functions. So they are able to understand how that the robotics is like coming to their own skins. So this is the shoulders rehabilitation case, and then the clinical study of stroke patient. So only 10 times of the trials, this is chronic patients, so basically it's not like that the easier to recover. But this 10 days at stroke, and we got that very good result. But also recently we did that also functional needs study, why they have that such kind of things. And then supplementary motor areas which can coordinate that also learning is significantly using this active type of that exoskeleton, not like passively controlled. So there are many of such kind of exoskeleton studies, but also we have very important like a prosthetics challenge. So I would like to share this beautiful Japanese the videos. Manami Ito, she's actually a nurse, but has got the car accident and lost her right legs. And some Japanese companies who made that wonderful prosthesis to use her left side of the shoulders to use the controlling of that right elbows. So very important things is, which is that not only the machine, as Vinyasa mentioned about that, active participation of people are very, very important. So advancing human capabilities through residual function is definitely needed, not only just by robots. So I am very interested in such kind of the human movement, and especially prosthetic study is for people with congenital amputee. Congenital amputee is different from the traditional amputees because only when she was born, already she didn't have that arms. So very hard about that. This is 6 years of that clinical studies. And she likes cat voice. So that's why this prosthetic hand also gives the cat voice when that image signals is exceeding. So the many kind of 3D printed different trials because she could very hard to get that to control the hand. But this is the first case is insurance covered because in Japan, child prosthesis is not like covered insurance, but there are some also limited case, and we got that successful to get that. So last one is the mobility challenges. So we are also interested in many of mobilities. Then the persons on the wheelchair are still forced to be seated. Not only the horizontal freedom of movement, but also vertical freedom of movement, we are challenging on that. Users keep growing year on year, but still that we have also technologies is trying to use challenges using passive mechanism and the user's center of gravity shift. I love passive mechanism a lot because it's easy to control. So there are many of the standing climbing wheelchair challenges. Also, even that the step climbing stroller is also the challenging. How we can use this kind of center of gravity shift is also very important factors. So this is one of the mark of the achievement, and this is the exoskeleton and the wheelchairs confinement. So he is able to stand up and sit down without any kind of actuators, motors support. Simply with the two spring mechanism with the center of gravity shift, we could able to that control. So the spinal cord injury is not able to control lower limbs, but still able to control these upper limbs in order to help the standing and sitting. So also, it is also even hard about that to carry on his babies. But this is the new way we are challenging to remove chair from the wheelchairs. And then there are many of the people who are participating in this study want to go to the supermarket, want to go to the library, buying a ticket at the stations. There are all the things is very hard only be seated. And also, we have a lucky have a chance to work together with the ODOS group and EPFL. So we really try to get these devices into the cloud, the people's the things. So last one is Cyborg Challenge. So after the assistance, we are also working on the wearable cyborg technologies. Because of that working on the robotics, I'm very interested in, so I found the difficulties how to get human intentions. So this is toward deep BMI technologies. So surface electrode of EEG from the brain is very hard. Spinal cord injuries patients are not able to get signals from lower limbs. That's why we are working together with the medical doctors to develop intravascular EEG signals. So inside in the brain, the 6 electrodes are placed. And actually, this year, first human study has been done. Then finally, we got the coherence of the inside and outside. This might be also possible, like the application to the perception and actions. So I think in the robotics technologies, with the aid of many other fields, we would like to go advance for that next steps. And for these kind of researches also, we need also the animal studies. So this is like that also as the Heike has presented, other 4 rat exoskeleton are existing. And then also ours one is available on this treadmill that the rodent studies for neuro rehabilitation. So one step by step, but still we would like to open the next step. But still, the advancing human capabilities through legislative function is very important, not only by robot, but active participation of patient users. I would like to appreciate all of those great effort. And also many faculty and collaborators here, and I would like to acknowledge them about that. Thank you for your attention.
Okay, questions? Yes.
Just a small question. Interesting talk, thank you. The standing wheelchair, I guess my question was, I think a lot of spinal cord injured patients have struggled with trunk stability, postural stability, so I was just curious if your approach takes that into account or compensates in any way.
Thank you. Also, I think we tried with the C5 that also patient with. And of course, simply to support with the body is also very important. I think C9 or C10, maybe less than that is okay without that support. But even if severe one, we are trying to with that body support. Thank you for important point.
Sure. Thank you.
Thank you.